Hi, today we will be presenting on municipal wastewater for indirect potable reuse. I'm Julia.
I'm Mira.
And I'm Matteo.
So to start, what is municipal wastewater? Municipal wastewater is that which comes from residences and is discharged into sewage systems. The primary component is human waste. And indirect potable reuse uses an environmental buffer such as a lake, river, or a groundwater aquifer before the water is treated at a drinking water plant.
In analyzing municipal wastewater, we look at three quality parameters. The three groups are physical, chemical, and microbial, and we'll be looking a little bit further into these in the next slides. Looking a bit closer into the physical parameters, we're concerned with four main pieces: pH, turbidity, total suspended solids, and total dissolved solids. To measure pH, we utilize a pH meter and determine whether or not it's acidic or basic. And we do this by measuring the hydrogen protons and know many organisms survive from a pH of 5 to 9. For turbidity, we perform a turbidity test before treatment by measuring suspended particles in the water using light. The goal is to have an NTU of less than 0.5. For total suspended solids, we measure the weight of a filter and pump the wastewater through that filter. We then dry the filter and measure the weight with the difference of weight from the initial to final measurements, identifying the amount of suspended solids. And for the total dissolved solids, we measure the electrical conductivity in an attempt to find the salt content. Moving on to our chemical analysis, the chemical parameters, the main subgroups are inorganic and organics. In inorganics, we know the salt from the previous total dissolved solid measurement from the physical parameters. For nutrients, we look at things such as phosphorus and ammonia, and these are mostly coming from urine and food extract within the municipal wastewater. In finding the phosphates, we measure them using an ion chromatograph apparatus, which basically separates ions with an ion exchange column, and it detects them with a conductivity detector. For ammonia, we use a colorimetric analysis with a blue tint, and the blue color is then measured in a spectrophotometer and is indicative of the ammonia concentration within our wastewater sample. Moving on to organics, the chemical oxygen demand the biochemical oxygen demand is measured initially, and a bacteria is added to it, and 5 days later, the oxygen demand is measured again. For the chemical oxygen demand, it is similarly measured initially. The dissolved oxygen is measured initially, and it is incubated for 5 days at 20 degrees, and then at the end of that period, there's a final measurement again. Moving on to microbial parameters, basically it is too costly to test for all bacteria or pathogens. So in municipal wastewater, we primarily test for fecal coliform bacteria from feces. And we do this by measuring indicator organisms because the fecal coliforms are some of the most harmful bacteria, which can lead to fatal diseases within our water supply. To find the coliform numbers, we run a volume of the wastewater through a filter and add that to a petri dish that has a food for the bacteria. And after several days, we are able to count the number of bacteria colonies in order to understand where the levels of coliform are at.
So after analyzing our wastewater sample within the various analyses, we were able to identify the principal contaminants of our water, which for the municipal wastewater was dissolved and suspended organic matter and specific organic contaminants. So within the three parameters, Physically, there was a high turbidity of 151 NTU. And if you recall, the desirable amount is less than 0.5 NTU for drinking water. There were also high levels of suspended solids. Chemically, our sample had a high chemical oxygen demand. And within microbial, our fecal coliform bacteria were above the detection limit. So in order to treat our wastewater, we had to identify the best course of action based upon the principal contaminants as well as the intended reuse. So the course of action that we came up with would be to add a coagulant to bond the suspended solids. And then an aerobic biological treatment, which would essentially provide oxygen to the good bacteria to allow them to eat the bad bacteria. And finally, we would use activated carbon to remove odor and taste contaminants, as well as some organic contaminants. So when we treated our wastewater, we used a coagulant of polyaluminum chloride, also known as PAC. And we added varying levels of the coagulants and then tested the turbidity. And based on that, we were able to determine the most effective dosage. And that was determined to be 50 microliters of the PAC. For the aerobic biological treatment, we added our sample to a bubbler, which feeds the good organisms, again, to allow them to eat the bad bacteria. And finally, for the activated carbon, we used a synthetic wastewater sample, and we added varying levels of the carbon, and then used a spectrometer to determine the most effective dosage. And that was determined to be 8 grams of activated carbon because it had the lowest absorbance in the spectrometer and therefore was the ideal quantity.
So looking at applications in Israel and California, currently San Diego treats municipal wastewater from neighboring Tijuana before it's released into the ocean. And we reflect on a statement by Abraham Tene, the former head of Desalination Division for Israeli Water Authority. He states that if California treated 85% of its water like Israel, then they wouldn't need desal technology at all. So we propose that California directly treats wastewater for use. Thank you.
Thank you.